Welcome to the next lecture for Introduction to Remote Sensing. This is my favorite lecture because it concerns Lidar, which was or is my specialty. Lidar is an acronym for Light Detection and Ranging, and it's similar as an acronym to radar, which is radio wave detection and ranging. But here we're using lasers in the visible and near infrared. Some lasers out in the mid infrared, but mostly near infrared and visible. And the thing that's special about LiDAR is that you can measure the elevation of objects on the surface of Earth, the elevation of those objects. And secondly, the second thing that's interesting about LiDAR and kind of unique is that you can not only see the top surface of whatever you're looking at, but you can also see under vegetation so that you can see the bare earth. And that's what I'm showing here. The top is a hill shaded digital surface model that is the maximum elevation model, and beneath it is a similarly grayscale processed bare earth elevation surface. So that's pretty much unique. Some people will argue that other systems can look beneath the canopy, but really LiDAR is the only one that can do it. And so it has a special place in remote sensing. So how does light detection and ranging work? Well, here's a little cartoon I sketched up. And at the top, you have a laser and a receiver. And a pulse of laser light is generated by the laser, and that light travels downward towards some object and then back up and into the receiver. And I know the light doesn't quite go into the receiver when it comes out, but that's conceptually what I'm trying to get across. How do we know the range? Well, the range is the time in seconds it takes for the light to be emitted, reflected, and then absorbed by the receiver. Okay, so that's the time. You divide that by 2 because the pulse has to take a round trip. It's got to go all the way down and all the way back. And multiply that by the speed of light. So it's basically the speed of light times the amount of time it takes for the pulse to be emitted and returned, and that gives you your range. So for instance, if you have a 6,667 nanoseconds, nanosecond is a billionth of a second elapsed time, then that's a 2-kilometer round trip distance, and that means there must be a 1-kilometer separation between the aircraft and the surface it intercepted. Now there's always a question about horizontal movement. So if the plane is traveling at 200 miles per hour, so that's 89.4 meters per second, in 6,667 nanoseconds, the plane's only moved less than 6/100ths of a centimeter. So not very far at all. And that's just because light is so tremendously quick. Now, the basic laser ranging method has been done since the 1960s, but it only became a practical tool in the 90s and really truly practical in the 2000s. Because suddenly you have available 2 things. First of all, you have GPS, so you can know where your plane is in 3 dimensions, and something called an inertial measurement unit, or an inertial navigation system, which allows you to know which way your plane is pointed. So, and that's what roll, pitch, and yaw are. Those are the 3 components of where you're pointed. So if you know where you are, you know where your plane is pointing, then if you know where the plane is pointing, you know where the laser is pointing. You combine that with the range and you get an X, Y, and Z coordinate on the surface of the Earth. And we sometimes talk about that as being a triplet. So what are the applications of LiDAR? Just very briefly to give you a sense of what we're going to be talking about. The primary commercial use of LiDAR remote sensing is in the collection of topographic data. So on the left, we have a hillside with typical pseudocolor illustration. So blue areas are low elevation, red areas are upper elevation. And at the bottom, we have the same thing, but for an urban area. So you can see not only individual buildings, but you can see their height as a color code. Other LiDAR applications that involve topography. Here we have the case of a landslide, and you might want to know, for instance, is that big chunk of the Earth going to slide again? Well, you can run a laser scanner over it and put that into models and tell whether or not it's probably stable or not. A lot of geology applications of LiDAR. Here's another one. So what I'm showing you there is southern Bainbridge Island in Puget Sound in Washington. And you can see, like most places around the Puget Sound, this is a very heavily forested area. You can't see the ground surface from the air. And this was data was collected as part of a project to look at microfaults. I talked about these very briefly. Microfaults are like faults, they're geologic faults, but rather than being large and obviously seen like the San Andreas fault, they're micro. They're small. There isn't much surface exposure of the fault itself. And so that we have a shaded relief image, and it's been illuminated from the south. And this is a 12-foot resolution DEM. And if you look carefully, sort of where the lower part of the island meets the northern part of the island, there's a white line, and that's the microfault. The interesting thing about this is that these faults can be as destructive when they give as something like the San Andreas fault. They're micro in size, but in fact they can have a huge impact, and the whole Puget Sound lowland area is shot through with these microfaults. And that's a big problem because Seattle, and again, I think we talked about this, Seattle was built on fill dirt that they brought in. And when jolted, that fill dirt can become plastic. That is, it becomes easily moved. And so Seattle is based or built on an area where a sharp jolt could lead to buildings falling down. So they wanted to have an inventory of all these microfaults, and they used LiDAR to get it. Another urban area, here it's been set up in sort of a wireframe, but you can see the heights of the various objects. You can see a bridge there near the center, and you can see some commercial buildings. My applications are forestry and forest planning. If you look at the top slide or top figure, you can see a power line in an area that's forested, and you have to maintain the areas beneath these power lines, because if the vegetation gets too tall, then you wind up in a situation where you can't go in to maintain it, or it might intercept one of those power cables. So it's actually worth it for these companies to fly LiDAR over the transects where the power lines go in order to figure out where to send their maintenance crews to cut down trees to keep the whole area clear. And here's a landscape where they've used LiDAR to identify individual tree crowns. So each one of those has been colored so that it's sort of got a unique color relative to its neighbor. So let's go through the steps in the LiDAR remote sensing process. The first thing you got to do is create a laser or LiDAR pulse. So what is a laser pulse? Well, laser is an acronym that I really like because it does what it says and it says what it does. It's light amplified by the stimulated emission of radiation. That is, there's some material, could be solid, can be liquid, I think it could be gas as well, and you're going to stimulate it somehow, either with light or electricity, and that's going to cause an amplified emission of radiation. So how does laser light differ from ordinary light? Well, it's monochromatic. That is, a laser emits in only a very small portion of the spectrum. You know, the spectrum, the color that it's going to emit is going to be only within a few nanometers of what you're expecting. It's intense, so in that narrow range of wavelengths, the laser's output energy can exceed that of the sun or any other known source. You can know this by just taking a laser pointer outside and on a sunny day and directing it toward the ground. You can see that the light from the laser is much brighter than the sun itself. It's directional. That is, a laser only emits light in a very well-defined direction, and it's coherent. So lasers emit light at only one phase. All of the phases of the light are stacked up so that they're the same. So why are any of these things important? Well, monochromaticity is important because you have this narrow range of wavelengths, and there you can put filters on that on the wavelength to block other portions of the spectrum, which means you're getting rid of background radiation or, for instance, backscattered sunlight. So that makes your signal clearer. It's also advantageous because we can precisely choose the wavelengths we want. So we might want to use green or near IR for various applications, and we can get that with great specificity with LiDAR. What about the fact that it's powerful, directional, low divergent, and coherent? Well, laser beams can travel long distances with little attenuation or power reduction. So this allows you to project them onto distant objects, like in application you might know of laser guided bombs, where you can light something up with a laser and a bomb will follow the track to that laser spot, and LiDAR remote sensing from airborne or spaceborne platforms. So we emit pulses of laser light from satellites that are, around 400 kilometers, and there's enough energy for it to go down through the atmosphere, reflect off the ground, and come back to the sensor that's on the satellite. Laser beams can be precisely aimed, so you can get specific targets or make effective scanning systems that move the field of view of the sensor back and forth, something that microwave radar systems can't do. In fact, for this application, microwave would be a better solution because it could penetrate clouds, which LiDAR cannot. But you can't focus microwave onto a precise enough spot, and you can't scan it backwards and forwards. So our old wavelength figure, This is showing you the range of wavelengths that are used typically in Lidar systems. So 1540, so out just beyond the near infrared. Toposys systems use this. Mid-IR is extremely, well, there's very little background noise in the mid-IR, and it's eye safe, so that's a good choice. Most LiDAR lasers, however, are in the range between 1047 and 1064 nanometers. And this includes Optech, the Aeroscan systems, Topi, Datus, Altimus, and I should mention Leica, the Leica ALS, Airborne Laser Scanner. These numbers are not arbitrary. They're based on what particular material you're using to laze with. And yes, that is a real word, laze. So certain doped silicon compounds will laze at 1064. So that's what you would have. 1064 is so an area that is high reflectance in both soil and vegetation. So that's a good choice and a popular choice among these sensors. For bathymetry, which is basically just the topography of surfaces underwater, we need to go and do something near the blue. And so what we do is we take the 1064 light and we put it into a frequency doubler, which is a little crystal that does what it seems like. Light comes in at 1064 and out at 532. So the frequency has been doubled, therefore the wavelength must be halved. 532 is half of 1064. And so that gives you the ability to penetrate water to some extent. So those systems generally have both a 1064 and a 532 nanometers to get at bathymetry. So you have one beam that bounces off the top of the water surface and one that penetrates down to, you hope, the lower surface. The ability to penetrate water is very dependent upon the turbidity of the water. So if you know what a Secchi disk is, it's a little tool for determining what turbidity is based on looking at a black and white disk and seeing how long you can see the black and white pattern as you lower it into the water. Most of these bathymetric systems can see to, around 4 Secchi disks. So you're doing a lot better than your eye, but beyond 10 meters or so, they can become unreliable unless you're in very, very clear water. And finally, there have been some systems that have worked at 900 nanometers. So like the FlyMap system works there. But again, in general, it's about 1064 for terrestrial observations and about 532 along with 1064 for bathymetric observations. So what about these pulses? Well, the technology for these pulses has increased incredibly. The lasers have gotten so they can emit more pulses in the same amount of time, and they're shorter duration. I just want to go over some general rules of thumb. So how many pulses can you create per second? Well, between 25 and 500 kilohertz. Now a kilohertz is 1,000 times per second. Therefore, you can get speeds up to 500,000 pulses per second. And that allows you to lie down a lot of pulses in a very short amount of time, which means that you can fly faster than you would with slower repetition rates. The horizontal pulse width, so as the pulse is leaving the aircraft, it can be as small as 10 centimeters. It could be as high as 150 centimeters. the vertical pulse duration. So the pulse is going to be emitted, and so at one part the pulse starts and then it ends. And that vertical duration can be between 6 and 12 nanoseconds. Now, that duration is associated with a depth. So for instance, the 6 to 12 nanoseconds is converted to a pulse depth of 1.8 to 3.6 meters. And that's because distance traveled by light in 1 nanosecond is about 30 centimeters. And that is equivalent in a two-way distance traveled to about 15 centimeters. That is, an object 15 centimeters away, the pulse will come back in 1 nanosecond because you're traveling, the light has to travel both ways. Secondly, the pulse isn't instantaneous. That is, the speed of the pulse, the power in the pulse is not uniform vertically. The laser sort of increases in power and decreases in power as pulses are being emitted. So what you have is within that column of light that's traveling down, well, in this case it's traveling sideways, but in a system it's going to be traveling downward. You have a distribution of power. So you can think of the x-axis on this graph as being time or space, and you have increasing and then decreasing illumination. And in the laser world, they strive for something that approximates a Gaussian pulse, just because it simplifies the math. However, we very often get a Rayleigh pulse. Same Rayleigh who discovered Rayleigh scattering. And in that case, the pulse takes a little longer time to decrease in power. And thinking that laser pulses are instantaneous or near instantaneous is probably the biggest misconception about Lidar, because as we'll see, it does have effect on how you interpret the data. So for instance, look at the graph on the left. We're just going to imagine that we have some kind of surface, and surface area is 1 unit. And there are 5 surfaces that are spread out, not overlapping in some area. We're going to get a LiDAR pulse from them. That is, we're going to emit LiDAR energy and record the amount of energy that's returning. And what you can see is, what you're going to get in your receiver is going to be the surface area of the object, sort of convolved is the way we would say it, with the pulse and the pulse power over time. So if that pulse is 5 nanoseconds long, you go to that next figure there, you'd expect that that's what your return pulses would look like. They're quite narrow. Although as you get to that last pulse at the bottom, you can see there are 2 objects there, and the pulses overlap. That's just because as the energy from one object is decaying, the energy from the other object is increasing. And so there's no point where you get back to 0. And as you go into the 3rd and the 4th panel here, what you see is that the wider the pulse, which you can also think of as the longer in time the pulse, the more smooth the signal gets. So that now, not only for those 2 panels, not only are the last 2 returns unable to be, you're unable to separate them. The last 3 returns are now such that you can't separate them. And that's going to change how we process or the result we get when we process the data from the Lidar. And that's just the same thing, but it's for Rayleigh shaped pulses. So not only is the laser pulse got a temporal difference in the amount of power, there's also a spatial distribution of power within the beam. So the beam is more intense near the center than it is near the edges. Okay, and this, again, in theory, the distribution is Gaussian. There's some lasers that have hot spots, and it complicates things. But in general, at least they're striving for a Gaussian distribution. Beam widths are generally given in terms of the width in which 86.5% of the total energy is found. So when they tell you that, it's 1 meter beam width, actually there's some energy that falls outside of that limit. In fact, there's 13.5% of that energy. So this means that the same amount of the same material intersecting the laser beam at the same angle can return different amounts of energy to the sensor depending on its position in the beam. If you have a small object and it's in the center of the beam, it's going to return more energy than if it's somewhere near this end or the edge of the beam. Okay, all of that was creating the LiDAR pulse. Now what happens? Well, the energy has to travel to the ground, and the laser itself is very directional. That is, you can point it. I mean, you have lasers that do topographic sensing that have like a 5-kilometer range. They're used in mining to figure out how much mass has been removed from a surface. So there are ones that go that far, and for that application, you probably want the beam to be the same diameter throughout the line that it's following. However, for LiDAR, you don't want it to be that compact. You want it to be spread out a little bit, both for eye safety and because you want to capture data that's sort of going to be averaged over a larger, what we would say is a larger footprint. The footprint being the intersection of the beam and the ground surface. So simple formula. As always, you don't need the formula, but I might ask you about how things vary. So the laser footprint width as it intersects whatever it's intersecting is equal to the altitude above the ground level times this gamma, which is divergence in radians. A radian is 57.3 degrees, and it's just more convenient to work in radians. So the beam size in meters at an AGL of 1,000 meters is the value of the beam divergence in millirads. So if it's 1,000 meters and you've got a 0.5 millirad divergent, then it's going to be, 500 meters. So that would be a bad example. So it's millirads that are used, and so that's 1,000th of a rad. So this is the part I need to come back to is you could have your laser in technically not have very much divergence. We have to spread out the beam to make it a little larger. So what happens when the laser beam hits a target? Well, if it just hits a smooth surface, it's just going to bounce right back and be hopefully recorded by the sensor. I say hopefully because it's possible it's going to hit a cloud on the way back or a duck. You never know what. Of course, I'm interested in vegetation, so I think about cases where you might have dense area of trees or a sparse area of trees. And the denser the trees, the more returns you're going to get from the surface of the canopy, and the fewer you're going to get from the land surface. And for vegetation, this is going to turn out to be key. So it's traveling down, it's going to interact with whatever surfaces it interacts with. And as we'll see, you can get the range to more than one surface for a given pulse. Now, this is an important distinction, which is that the LiDAR cannot go through materials in general. If something was highly transparent, it could. But in general, it's not going to pass through objects like, for instance, leaves, but rather it's going to penetrate through the canopy. So it's not penetration through the leaves, it's just these tiny areas within the canopy where you have a direct line of sight down to the ground. And, the laser emitting photons, various things can go on with the photons. They can either be bounced off of the surface and returned to the sensor. So that's canopy penetration. You might have multiple scattering events inside the canopy, although those are probably pretty rare, or you can have photon loss. So the problem you run into is, let's just assume for the moment that the height of the first object that's encountered by the laser beam, the height or the range, you could think of it either way, is the only information recorded. As you increase beam size, it's going to reduce the penetration of the canopy, because if you can only measure one range, then whatever it hits first, all the energy that's going to be seen is from that first return. And therefore, you're never going to hit the ground, or you'll hit the ground a lot less frequently than you would otherwise. And this is important because, for instance, for trees, you need to have two elevations in order to get what you're interested in, which is generally metrics related to height. If you don't get the ground surface, then you're not going to be able to get that elevation, and you're not going to get the height of the objects themselves. And then the one other thing that can happen with these photons, and most photons suffer this horrible fate, which is they're scattered off in directions that don't allow them to get back to the receiver. So they came so close, they were in a laser, they were emitted from a laser, they hit a target, but then they were reflected off in all sorts of, or scattered off in all sorts of different directions, and no longer could contribute to the LiDAR process. Okay, so we've created a pulse, it's traveled to the target, it's interacted with the target, then it travels back to the sensor. Now about processing of the return signal. So you can imagine laser illumination. They're shown in a green beam, it's labeled at top, passing down through the atmosphere, and then interacting with a branch that has some foliage in it, and then interacting with two dead branches, and then interacting with a little shrub there, and then the ground surface. And that return signal we refer to as a waveform. Okay, so the more material that the laser pulse is interacting with, the more power that's going to be returned. And so that's the return signal waveform, and we will return to this in figuring out how we're going to process this return signal waveform. Now, the simplest thing you can do, in a sense, is simply record the entire waveform. And this is work that I did when I was doing my PhD. So you have some energy being returned. the first energy that's returned, that is the energy from foliage closest to the top of the canopy. So that's going to be the top of the canopy. It's going to be, below the sort of background noise level of the Lidar receiver. It's going to increase past that. And then you're going to have a fairly rapid increase in the amount of power that's returned. And that peak of those returns, where, in this case, where the travel time is about 60 nanoseconds, or the distance there is normalized to the top of the canopy, is about 20 meters. That peak is generally what we think of as canopy closure. That's where the variability of the upper canopy surface has been reduced, and you've got all canopy. And then the power that's coming back is decreasing. That's not because the amount of stuff in the canopy is becoming lower. What it means is that you already return a big chunk of the number of the photons, and the power is decreasing because there's less and less source energy to be returned. You might see a nice little gap there, like at 110 through 130 nanoseconds, where you have a lower foliage in the lower amount of foliage in the understory. And then in this case, we see a little bit, maybe a meter or two of increase, and that could be understory vegetation. You then hopefully get some kind of ground return. So some fraction of the energy gets through the entire canopy and is returned by the ground. Because the ground is a solid surface, you're going to get return energy that's generally greater than you would get from the canopy. And so I've colored that in as brown. It wouldn't be colored in brown. You'd have to run some statistical analyses to figure out where the ground return is. So that is what I consider to be the sort of simpler thing to do with the Lidar pulse, is just record all the energy that's being returned. And there are a lot of commercial systems now. Research systems tend to work that way. There are a lot of commercial systems that work that way now, but they're still mostly using what we would call the discrete return method. And that is, instead of digitizing all of that energy, what you're doing is, picking out a few heights that seem to be important. And the first type of lasers used only first returns. That is, you see the threshold there. As the energy that's being returned passes that threshold, becomes greater than that threshold, a return is being noted by the receiver. Later, first and last return sensors were developed. So you get that first return, and then the forward edge of the last return, when you increase past that threshold, that is also recorded. Why the first and the last? Well, because if you're looking at things like vegetation, what you want is, you want the height or elevation of the top of the canopy and the height or elevation of the ground surface, and that's how you get them. More commonly these days, you have multiple return systems. So you might get 3 returns or even 4 or 5 returns. Curiously, you won't get if you run out of returns in the canopy, so like it's a highly variable canopy, you're recording 4 returns. If you don't get all those returns recorded, that is, if your digitizer can't record more than the number of returns you have, it just drops off the last return. And this is where we get to the problem that we talked about in terms of the pulse length or pulse duration. That is, if you I've put in more trees here at the bottom of this figure. If you have foliage at the bottom of the canopy, for instance, that's going to occlude the ground surface. And so there's going to be more power in that range of heights. And so you're no longer seeing the ground surface, you're seeing this new surface indicated in red. And so your height is going to be, your last height is going to be moved up. And this is, you'll see, a major problem with using Lidar. And this is an example. I like this because the person who developed this came up with a great name for it. So in the upper left hand panel, what we have there is a shaded, hill shaded map of the elevation of a Lidar surface, from a Lidar surface. And then at just to the right of that, we have an image where we have the, again, hill shaded DEM from the raw or bare earth, I should say raw DEM that has been processed to take off the upper canopy. Okay, and if you look down at the lower left-hand corner, we have a graph. It's that little transect location that's marked in either yellow or red above it. And what we see is the top upper canopy surface in red. And then what we're thinking is the ground surface in yellow. The fact is that's not the ground surface, okay? If it was the ground surface, we would think that the upper vegetation would more closely follow it, or vice versa. The ground surface would more closely follow the surface in terms of its variability, not in terms of its absolute height, but in terms of the relative height. But in fact, what you've got there is a situation where you're not getting the real last return. You're getting some other return out of the system. And I just like the fact that the guy who did this was like French Canadian, and I'll butcher this, but he called this les moutons. And because he thought they looked like little sheep grazing out in the forest. I always thought that was funny. So, as I was saying, increasing pulse width or duration has the effect of increasing the height of the topographic surfaces developed using data from a leading edge detecting LiDAR. So that's a major problem. Here you see the waveform being smooth, and it has the same effect as having vegetation in the bottom of the canopy. That signal, because it's smooth, never goes below the threshold, which means it never can then be in the position of increasing over the threshold, and so it's not marked. And so that last return therefore gets bumped up to where I'm showing the red line. And there are various different ways of dealing with this problem. Like the figure I was showing you before, you can just record multiple observations or multiple discrete returns. You can have two thresholds, okay? So you can record both the leading and the trailing thresholds of each of the returns, the return energy. You can then average those together to get a multi-threshold approach with a centroid instead of the leading and trailing edge. And you could do photon counting sampling, and that's a relatively new technology where you can record the travel times of individual photons. So it's very, very sensitive. It's got its problems with background noise because it is so sensitive, but it is an approach people are using now. Some of the differences between waveform recording and discrete return LiDAR. Um, Waveform recording is not subject to signal processing errors. So in the discrete return case, you've got um, the receiver basically making decisions about what ranges are significant. And with waveform recording LiDAR, you just collect all the data. You can make those choices and select thresholds and that sort of thing in the lab, and you can adjust these things. In a discrete return system, that's all going to be determined for you by the receiver itself. It has an enhanced ability to characterize the canopy structure since it's getting the whole thing. It has the ability to concisely describe canopy information over large areas. Very often you don't want the number of points you're going to get per meter squared, because these days they fly with crazy numbers like 12 points per meter squared, and that's just a lot of information to process. Very large files, you know, data sizes, you know, file sizes at around, you know, 100 gigabytes or 500 gigabytes. And there's global data sets that have been collected, the ISAT program, and then currently the JEDI program, which is Global Ecosystem Dynamics Investigation, which is a LiDAR that sits on the ISS, International Space Station. I really begged and pleaded for them not to call it JEDI, but what are you going to do? Remote sensing scientists are a bunch of nerds. The advantages of the discrete return system: you get higher spatial resolution, you get smaller diameter footprints and higher pulse repetition rates, and you do get a certain flexibility in data processing because you have so much data to work with. But the biggest advantage is availability. Commercial systems in general have been this kind of system, although some people are changing over to commercial waveform recording systems. But, you know, you can get these essentially for waveform recording systems. These have been research systems, and discrete return has been commercial systems. Again, that's changing to some degree, but you'd still probably get more discrete return systems that you could purchase data from, or purchase a data collection flight from a commercial vendor. And here is just a nice comparison of discrete return and waveform recording LiDAR, what you would expect. This is actually at the Wind River Canopy Crane, which was kind of a crazy project done where they actually put a construction crane out in the middle of a Douglas fir western hemlock forest, and you could ride around in a little gondola. And I've done this. You ride around in it and you see the various parts of the canopy. And there was a lot of good science done there. And there was also my work where we mapped the surfaces of just a couple of trees here that you're seeing, and also simulated what a waveform would look like. Okay, so we have processed the return signal either by looking at a waveform or recording a series of pulse returns. We now have to scan, because so far all we've done is emit one pulse and record the information from the backscattered radiation from that point. So the way we do this is by scanning, just like the cross-track scanners we've already talked about. You either have an oscillating mirror, so the mirror is the dark line there in the upper left-hand panel, and light is coming in from the left, and that mirror is being rotated back and forth so that you're scanning different points on the ground. And there are a variety of different systems that have different ways of moving that mirror. The simplest thing you could do is what Leica does, which is it's sinusoidal. That is, the mirror, it actually slows down as you get to the end of one of these traces, whether it's the far left or the far right, because you're looking at this in sort of plan view, these points on the ground, and then it speeds up as it's near the center. They do that because if you don't, then the mirror itself can break, because it's going, if you stop it, you're going to have just immediately stop it, you're going to have serious problems with mechanical stability. So that's one approach. You can make a sinusoid. Optech, another big manufacturer, uses a Z pattern. So in this case, you're drawing a line with equal spaced Lidar observations and then drawing it back and forth. There have also been parallel systems. In this case, you just drive it forward and then drive another line forward. You don't use the back motion. And this is a type of scanner I like. This is using a rotating polygon. So that's a mirrored surface on the edge of that polygon, and that's going to give you the parallel observations that we were looking at. There are lots of other things. There have been fiber scanners, so the laser pulse is directed into one or another of a line of optical fibers, and so they go one after another, and what happens is you wind up with these beautiful lines of footprints on the ground. There's also the Palmer scanner. The interesting thing about the Palmer scanner is you look forward and you look backward at the things you're flying over, and so you have a chance to get two observations. And if you're doing work like on ice sheets and you have crevasses that you really need to get into in order to understand the topography, this gives you two chances to get in the crevasse, depending on where the plane is and whether the scanner is looking forward or back at that time. So this is just to show you the conventional Z pattern used by Optech sensors. That yellow line is the flight line of the plane, and you're going back and forth with these pulses. One thing to note is when you purchase LiDAR data, they will say, we're going to get you 12 shots per meter squared, which sounds great. But in fact, if you look at it carefully, what you'll realize is that there are large areas between each of those cross-track swaths where there's no data. So there isn't one number that can describe the number of returns on the ground surface. There's a distribution. Some areas have more, some areas have less. And that's just something to keep in mind. As in aerial photography, you need side lap between data passes in order to assure that you have complete coverage. So in the upper right hand, what they're showing you is that dark blue area. That's where you have two lines or two transects overlapping. You have double the density. And that can be very useful. For instance, for quality control purposes, you have a red colored pass and a green colored pass, and if you compare your results for each one, in this case there's a 1 centimeter difference between what the elevations are in one pass and the next pass, and you can use that information to correct that data. One important factor when looking at LiDAR is to check out what scan angles they use. So common sensors are capable of scanning across 14 to 75 degrees. Now that's two-sided. That is plus or minus 7 degrees and plus or minus 37.5 degrees. In practice, that kind of large scan angle leads to problems with the resulting data. And so they do so because you're no longer hitting, it's like displacement. You're no longer hitting the top of the object. You're getting data back from the side. And similar to, the distance from nadir, that is a big effect in displacement. The scan angle here is the factor that leads to the most error. So you want to keep those scan angles narrow enough that that effect doesn't overwhelm the other effects in the data. So if you wanted to extract the ground surface of crowded areas with buildings in the city, you can probably go up to a scan angle of plus or minus 10 degrees. If you're looking for a ground surface in, say, a coniferous forest, a scan angle of 45 degrees maximum, two-sided, is what you want to do. And some would say that that's too much. Unfortunately, the narrower your scan angle, the more passes you have to make, because each one of your swaths is going to be smaller. And so you have to fly more, and that costs money. So there got to be some compromises.